We discuss differential analysis of fluid flow, and when we say differential analysis of fluid flow, we mean that we want to discuss the differential equations of motion that depict and that reflect the fluid flow motion, and the solution of which will result in the fluid flow behavior. So there are various things that need to be discussed. Some of the things we did discuss initially, the preliminaries, but I am going to review some of the things, for example, in derivation of continuity equation, and then onward we will be deriving Euler's equation, what we call as momentum equation also, the Navier-Stokes equation, and so on. So step by step we discuss all these things, and in the process we will also see the special cases, whether the body, the fluid, the motion is a steady motion or unsteady motion, the fluid is a viscous motion or inviscid motion, or the fluid is, for example, it has the stresses or it doesn't have, and so on, whether it's an ideal fluid or not. So all these conditions are subsets, but generally we try to see the equations, and we go over some of the things once again. So, and differential analysis is a broad meaning by that we derive equations of motion in a differential form, at the solution of which will tell us how the fluid is going to behave. And of course, with that are connected the type of fluid behavior that is involved, whether it is in a rectangular motion, cylindrical motion, whether it is taking place in a pipe or in an open channel, and so on. And the boundary conditions also will apply. What are the boundaries at the time where the fluid is moving? So all these things have a role to play, and we try to develop the equations. For equations, we need to use the rule, the formula of one, the rule of the mass conservation, and similarly the Newton's law of motion, the second Newton's law of motion, which is F is equal to ma. So all these things help to derive the equations. And in the process, we understand how the differential equations of conservation of mass, which will lead us to derive the equation, a continuity equation, and the differential linear momentum equation are derived and applied. The thing just that I said. And from continuity equation, it helps us to derive and to find out the stream function, the pressure field, the streamlines. We can plot them, we can see how the fluid will flow, how the streamlines will look like, and so on. Analytical solutions can be determined for simple situations. For more complicated, real fluid situation, the solutions are not so easy to find. But analytical solution can be determined for simple flow conditions, as we will see in the later part of these discussions. The differential analysis, on the other hand, involves application of differential equations of fluid motion to any and every point in the flow field over a region which we call as a flow domain. And of course, the boundary conditions. I have mentioned these things already. And if the flow is, for example, unsteady, we must take the change in motion with respect to time, the variation that takes place with respect to time. So that will be time dependent, and if the motion is steady, we will eliminate the time factor from that equation. But in a generalized form, we have to keep the time variation in our equations, because the velocities or the behavior of the fluid may change with time.